Good morning. Today we go on with our examples of different types of cable-stayed bridges, and today we come to two very important examples for series of cable-stayed bridges. You will recall that in the earlier parts we had one lecture on the general theory of series of cable-stayed bridges, and today we have the two most prominent examples which exist today of series of cable-stayed bridges. In actual fact, these are the Millau bridge, which we have mentioned before, and the Rion-Antirion bridge. Both under very different conditions show different solutions. Just to recall briefly, a series of cable-stayed bridges are several main spans, one after the other, without the usual side spans and hold-down piers there. So, series of cable-stayed bridges have two main problems to solve. The one problem is how to stabilize the tower tip, because there are no hold-down backstay cables. And the second is, because of their increased length, how to cater for the changes in length in the beam due to temperature, shrinkage and creep and so on. We have here one example to show the load transfer of a series of cable-stayed bridges. The load is in one span, and so the other span deflects upwards because there's not the hold-down pier to hold it down and to keep those in place. This example shows what happens if we do not take into account the bending stiffness of the tower by introducing a bearing underneath the beam. Here we have even bigger deflections if we have bearings than when we use the bending stiffness of the tower. But this is a picture you should remember. Loads in one span mean, from the start, large upwards deformations in the other spans, and those have to be limited. Now, we start with the Millau bridge as one example. The Millau bridge closes a gap in the second north-south connection in France. We have here the National 7, Paris-Lyon, and that's the one westwards. And before this bridge was opened, every summer there were long queues of holiday travelers because there was a road through the valley. And finally then, after many years of discussions and planning, it was decided to use one large long bridge right on top of the landscape and not go down here. But this meant that we have to go, that we are 270 meters high above the valley, and finally it turned out the most economic is 342 meters. Now, 270 meters is a lot. I mean, somewhere I've seen a picture that you can put the Eiffel Tower underneath here, just as an example. Or, from my personal experience, for many years I had been working intensely on the highest bridge in Europe, the Kocher Valley Bridge near Stuttgart, with 180 meter high piers, and this record unfortunately then was taken by the Millau Bridge with 270. So, the engineer for the Millau Bridge is my good friend Michel Verlejeux, one of, if not the leading French engineers. We've mentioned him on the Normandy Bridge, where he was in charge also, and he helped you last year with your travel to France to visit bridges, because I had asked him. He made his diploma at the École Nationale des Ponts et Chaussées, and later was a professor for structural analysis there. This is the top elite university, one of the grandes écoles in France. Excellent education with heavy emphasis on mathematics, much more than in Germany. And we know him for the Normandy Bridge and for the Millau Bridge. He was also in charge of the Vasco da Gama Bridge, which is in Lisboa in Portugal. He was kind enough to give me his slides. So the slides you are seeing are those Michel Villageux used for his lectures on the Millau Bridge. So we have here, as I mentioned, 270 meters above the valley, highest bridge certainly in Europe. I'm not sure anywhere in the world where there are higher ones. And it turned out 342 meters is a reasonable distance. Of course, one has to weigh the length of the spans, which costs money, against the number of piers, which are the more expensive, the higher they are. So that's the compromise. It's interesting to note that the original design was a concrete cable-stayed bridge, done by the famous German engineer Helmut Homburg. I showed his picture to you with the Bonn North Bridge, and I have the results of his design for the Breton Bridge under my examples of general moments in cable-stayed bridges in lecture 9, if I'm not completely wrong. And I've noted there, this was the concrete design for for this bridge. However, the contractor came up with an alternate, which was Eiffage, the company founded by Eiffel, major French steel contractor, and it was more economic, so the steel alternate was built. We see here the cross-section. We have a central box, also for the construction by launching. We will see that in detail. And we have these inclined webs for, say, aerodynamic shaping, because at that height, winds are a very important load, and we have to reduce them by streamlining the cross-section. The construction of the piers themselves show the special characteristics of the Millau Bridge. In longitudinal direction, in a driver's view, we have just a cantilever, concrete at the bottom, steel at the top, with a more or less rounded cross-section. The trick and the unique characteristic of the Millau Bridge lies in the side view or elevation of the towers. And here we solve the two problems, how to stabilize the top and how to take up the movements. We stabilize the top by using an A-tower, an A-shaped tower on top, and you remember I've given that to you all in detail, that an A-shaped tower is very stiff, takes the cable forces in compression and tension, not in bending. So we have a stiff top. Now, what to do with this force couple, tension and compression, which comes down here? Well, we receive the spread tower legs by spread pier legs. You see here the pier has a slot, a cut in between, and so the force couple from here goes directly into a force couple here, which is again very stiff. And only in the lower part the force couple then becomes a bending moment. So we have stabilized the tower top by A-frame. How? So it's a very stiff tower for cable loads, lateral loads. On the other hand, because by providing this slot, we halve the cross-section, and by that we reduce very strongly the stiffness. You remember the stiffness goes in with the third power of the depth, and if we reduce that by half, we have 1/8 of the stiffness in longitudinal direction, just by taking these walls out. So the piers are in transverse direction soft enough, flexible enough to deflect and follow the elongations of the steel beam due to temperature. So you must remember a very elegant, I'd like to say French solution, combining the required stiffness against overturning from the cable forces with the required flexibility for the longitudinal forces. Quite unique, admirable. Now, we have here 240-meter high piers built by with jumping forms. It looks a little bit difficult, the cross-section, but they change alternately, and so finally the shape has been refined so that it can be done reasonably with jumping forms, although the dimensions of course change. Now, after we've built the final piers, we come to the beam. The beam, as usual, is prefabricated from its element, basically stiffened plates. We have an upper or outside plate and stiffeners, troughs, which are in there. That goes around. They are fabricated, then they put together, partly I think at Fos-sur-Mer in the south of France, near Marseille, transported to the site. And as elegant as the design for the final stage is, as elegant is the construction method. And for that, Jean-Marie Crémer, a Belgian engineer, was in charge. We have met him before for the Ben Ahin Bridge in Belgium, which was rotated in, you may recall. And he did the construction engineering, quite extraordinary, for the Millau Bridge. First thing is the bridge was to be launched. Then he said we use on each final or auxiliary pier 2 rows of bearings with a distance of 20 meters. Well, I mean, 171 meters to 151 meters doesn't sound much. But we all know the moments go in squared. So if we take the ratio of the squares, we come to 78%. We reduce the moments during launching by 22%. And when we have in the final stage 342 meter span with 4.2 meter deep girder, 1 in 80, that's not too extraordinary for a cable-stayed bridge, quite usual. However, if we think of the cantilevers during launching, we come to 100, half of it, minus 20, 151. So we come then to a slenderness of 1 in 35 for the cantilevers. And that's quite unique, how to overcome that. We see here we need, for the 342 meter spans we cannot launch, we need auxiliary piers, and on top of each we have the sliding bearing plus push bearings, which, so to say, push back the auxiliary tower head so that it remains in place during launching. Otherwise the friction forces would turn over. The auxiliary piers may be even the final piers, and that's the construction on top there. The next neat thing here, quite unusual, is the contractor wanted to save the costs for digging away this part of the, say, beginning or end of the road, which would have to be filled afterwards, because this is the level of the final bridge. And so if we normally have the fabrication and launching, we dig it out, push forward, and afterwards we have to fill it up. Said, no way. And so they had the launching up here, and 4.2 meters let the bridge bend. And it did. And we see it here in this shortened view, how 4.2 meters, the bridge beam, can deflect between, say, the abutment and the first pier. There is at least one movie out where you, in a very skew angle, where you can see it, and I always compare it with a snake, how the thing winds down there. So, of course, when you calculate it, it works, but you have to come up with the idea, and I thought that's an extraordinary feature there, just to save money. Now, the launching starts with an auxiliary pier here. Of course, we have, as for all incremental launching, a launching nose, a light steel truss, which we put on top to reduce, again, the cantilever moments. And then comes the next unique characteristics, which, when I learned about it, was quite stunned. They used the first tower as support for the tip. Well, it has been done before. We've done it for incrementally launched concrete bridges. It is rather tricky, because to cater for this load when you transfer the load from here to there, it's not so nice. But apparently you could do that without additional supports. The towers were shortened, not the usual 90-meter towers, but only 70 meters, because the wind on the 90-meter high towers would have been too much. So in order to reduce the wind, that was lowered. But the main trick, which puzzled me, was that they, after the cables are installed, during launching, they do not adjust the length of the cables, which would make that very tedious. It is possible with the given length of cables, sometimes they are very stiff, very much stressed, and sometimes, as here, they are slack, and all that has to be calculated for every 2 meters of shifting, I can tell you. It's a lot of work. But apparently it works, and I would not have believed that that's possible, but it is possible. So that's another very elegant trick. And so we see here the launching in full flow. We have here in the main spans, we have auxiliary piers. We have here the launching nose, and we have here this auxiliary tower, which here it so happens stands just on top. That's the way they launched the, 1,250 meters something from each side to come to about 2.5 kilometer long bridge. Now when we reach the town, thank God we do not have to place an auxiliary pier into the river, because we can do 1/2 from one side and 1/2 from the other side. So we don't need an auxiliary pier there in the center span. Here is again an example where it so happens this auxiliary tower sits on top of an auxiliary pier, but that's temporary. It moves along and the beam can take it. We come then close to the closure joint to adjust very carefully. Of course, it helps here immensely to be able, in this case, to pull at the cables. You know, you normally, with that cantilevers, 170 meters each side, you do not come exactly, you need to be in level, and you have to have the right angle. There are bridges which are welded together with a little kink if you look along, but you don't want it. And so you can adjust the tips, the elevation as well as the inclination by there pulling and adjusting the cables. Very neat solution. And finally here we have all the beam installed. We see the 2 auxiliary towers at the tip, close to one another. Here the main span without the auxiliary pier. And now to install the final towers, just showing here we have the cable anchorage, 1 cable plane in between this steel box, and then the 90-meter long towers are moved across the completed bridge. It was, forgot the number, it's in the script. It was a very high load, which was a test load for the bridge itself. It will never see again in its life such a heavy load on the beam as the transportation of the tower involved. Then the tower was rigged up, put it vertical, and placed in position. Of course, the auxiliary towers at the tip had to be lifted to put on the missing 20-meter basic parts. So, this was the Millau bridge. The main items, what I call elegant design. In the final stage is the tower, a steel tower on top, and the split cloth pin, Wäscheklammer, I like to call it, cloth pin design at the bottom where the 2 A's come together, very stiff against moment. On the other hand, by cutting a slot into the piers, roughly we have 1/8 of the horizontal resistance. So we have very flexible piers so that they can move with the beam in temperature. And construction, the launching itself on 342-meter end spans is something. Then we launch 4 meters too high to save the money and bend it down. And we have the final towers modified as auxiliary supports at the tip. Those are quite a number of outstanding ideas coming together in one bridge. Normally, everybody is quite proud if he has one good idea, which he can apply in a bridge, but they had several here, so I admire that very much. This was the first example, Millau. The second is Rion and Tyrion. Greece, we roughly have an idea where that is, and so we have here the mainland and the Peloponnese, and then we have here the little towns of Rion and Tyrion. So it goes across where the Gulf of Patras and the Gulf of Corinth meet. Now, the final bridge is quite beautiful. Remember the Millau bridge, series of cable-stayed bridges. They are designed properly with clear lines, tend to look very beautiful. Of course, especially if you take the deep blue sea and the white cables with the whitish towers, it's quite looks like a sculpture, like a work of art. The problem here for Rion and Tyrion is the very high earthquake. Similar, by the way, as for Messina, where I've been working on the earthquake. It's a problem. We have here very high accelerations exerting forces onto the bridge. But in addition, we have to consider up to 2-meter movements of the soil in case of an earthquake. It doesn't only shake backwards and forwards, but it can move. And 2 meters is a lot. I mean, how do you cater for a movement of 2 meters in a bridge? And not necessarily the whole bridge in one go, but between 2 towers, if you have the fault there. So that is the main problem here, which had to be solved. We were also doing an alternate there, and considering that there are all sorts of considerations. So it's a real problem, and they have a good, elegant solution. I'll show you. Here was another Frenchman, Jacques Combeau, friend of mine, well, like Michel Verlogeux, also professor at the École Nationale des Ponts et Chaussées, and he was very much involved together with Jean Muller for the Breton Bridge. We have met him there. You may recall the Breton Bridge in the development of concrete bridges, 320 meters, 1977, I think it was done. And besides all sorts of other things, he was in charge of the Rion and Tyrion Bridge. Again, I have to thank him. All the slides are showing are his. He was kind enough to send me his slides, which you don't do for everybody. But he got mine on other occasions as well, of course. Now, well, it cuts both ways, naturally. We have here the main items. We have here 3 main spans with, or you can say 4 towers with, in this case, 560 meters. The span is longer. Can very easily deduct that, because the foundations here, piers and foundations, are even more expensive than for the Millau. Millau, they were very high. Okay, cost money. But with sliding forms or jumping forms, it's not so bad. But here, we had to make them fit against the earthquake, which made them per unit even more expensive in relation. And the more expensive the piers become, the more overall economic it is to make the spans longer. I think that's a very basic issue. Now, each unit consists of a solid, rigid pier with a total length of 560 meters beam supported by stays. We have here the cross-section. I would nearly say an American cross-section. That's the way we designed our bridges in the US. Open cross-sections, not boxes, and a composite bridge deck, because they also have a problem with welding, apparently they're in Greece. So that is the most economic solution. And how now do we take care of our 2 main issues? Keeping the tower head in place and accommodating the beam movements. Keeping the tower head in place, I do it on this, we'll see it later also in some detail. we do in two ways. We have A towers again on top, similar as we had for Millau. In this case, it's a four-legged A tower, so it's transversely also A shape. And then we have a very solid pier underneath. So the bending, the fourth couple which comes here, is taken in bending in this pier shaft. And then the pier shaft has a foundation which is circular, wide enough so that it is a raft foundation. It's a flat foundation which sits directly on the soil. However, the soil is very specially prepared, and there's then the trick with the 2-meter sliding. The beam, again, you have seen that quite often with my lectures. That's the type of composite beam I prefer. We have a steel grid with open cross sections, keep it simple, and then we have a concrete deck on top, either precast or cast in place. They have a little trick here, I'll show you later. It's cast in place, but before lifting already. So that's typical. We have web extensions, which I showed you were first used for the Hooghly River Bridge and then for Enesys, which takes the forces directly into the webs. All very good and thought out. But the real unique part comes now. We know the tower on top here, but now we come to the soil underneath, where there is a trick. We said we have here, I think it's 30-meter diameter something, it's in the script, a hollow truncated cone, if you want to call it like this, which is stiffened by transverse walls and an inner wall. And from the bottom up, after dredging the top layer of clay and mud and dirt away, there is, I think, a 2 meters thick differentiated layers of gravel, starting with rounded river gravel, going to broken gravel. So there is a stepping of the inner friction. And then underneath this layer of differentiated layer of gravel, there are steel piles, but they end at the top of the soil. So they are not piled foundations, but they just reinforce the soil underneath, but they have no connection to the foundation itself, not a piled foundation. It's a reinforced earth in effect. And so what happens now if we have here the it doesn't see it so well, look at my hands. We have here the bottom of the foundation, and then we have here the reinforced soil, and in between we have about some meters of gravel. And if we have this relative movement of 2 meters, then the movement shall be taken up by a movement in the gravel layer. So it's a plastic deformation within the gravel layer. It's not the first application at all. I've given you the reference, but it's the first for bridges. I think it has been done for buildings or so something, but it's the first time. And it has been also used, you may recall the Golden Ears Bridge in Vancouver, BC, which I showed you. It's an extra dose bridge by Bilfinger, lately completed, where I was checking engineer. And they have also taken this because there's also the earthquake. Plastic movement within the gravel layer to take up the up to 2 meters. I mean, what can you do? You can't take up 2 meters in a beam. Then you need sliding joints, and you don't want that. So that's the trick you should remember with the Rion-Antirion bridge. Production was also thought out quite nicely. We have here a floating barge with all the driving equipment and so on anchored to concrete blocks at the bottom. And then, first of all, these steel piles are hammered in. The mag has been taken away before. And then we have here this layer of gravel and tower foundation hollow up to here, and then we have the 4 tower legs. I've told you that. And how do we produce that? Well, we use a dry dock. You know, a dry dock is traditionally used for building ships in the dry and then floating it and float the ships out. And for the oil drilling islands in Norway, this technique has been quite often used, so it's also applied for bridges, nothing really new. And we have here, and also a little trick, quite remarkable. They used a dry dock which could accommodate 2 foundations at a time. We see here the first, and then we have here the cofferdam, you know, rammed sheet piles to keep the water out. That's how it's done here. And then when we have the bottom foundation part done and have started with the pier shaft, then the cofferdam in front is taken out and the dry dock is floated, and the bottom foundations float up. So the first one, which is a little bit ahead, is towed out. The next one comes here, and then the third one is to be built afterwards, built in a staggered way. However, normally one would say, well, then we have to close the cofferdam again, which means a lot of bringing down again the sheet piles. It takes a long time, it costs a lot of money. And somebody had the bright idea, no, we use the first foundation as a gate to close temporarily the dry dock, pump it out again, build the next one, and so on. So by using the front foundation as a temporary gate for the dry dock, they saved a lot of time. Just a little smart trick. Then during floating out, we see it here, the pier shafts are built up. Normally then the bottom sinks down either by the additional weight plus floating with water until it's towed into place. We have here the prepared foundation with the piles and the layer of gravel. Lower it down. And once all that is done, we build by free cantilevering the 4 tower legs, connect them, I've shown that to you several times, against the bending moment, plus also during each construction stage a major earthquake had to be taken into account. And if you have here 4 cantilevers, I don't know, 100 meters high, you better connect them very strongly if you want them to survive an earthquake. Here is the steel part. It's a steel composite cable anchorage. Steel part is put in, which is then cast in to concrete. We've seen that before. Here we have a steel box, so to say, where the cables are anchored, which is placed on top of the concrete and then cast in. You've seen that several times. And then once all this is in place, we start free cantilevering. In this case, it was done in parallel for all the towers. We do it by floating crane. We have here one element arriving. We see it here a little bit better, and that is another special item that this is the only example I know where it has been done, where that Kapshui Mun, but that's a little bit different, where we have the steel grid plus the concrete slab on top, lifted in. It helps a little bit with construction time, but of course I lose the big advantage of having to lift only, say, 60-ton steel grid and the concrete in pieces, or this weighs about 270 tons. But apparently they had this huge floating crane on site, and that thing didn't mind whether it's 60 or 270 tons to lift. And so this was then easier to do. But it's an exception. Normally, if you lift from the beam, you battle for every ton and would need more auxiliary equipment if you voluntarily go from 60 to 270 tons. Concrete precast elements, they weigh up to 300 tons. Well, you cater for that. But if it's not necessary, you'd rather not do it. Except you have the floating crane, so to say, for free, because it's there. Here we see then in parallel free cantilevering, similar, and the completed bridge. Now, briefly, earthquake. Your followers will have, with dynamics, a little additional lecture on earthquake. We've amended that. Basically, we have always, when we talk about earthquake, we always have that response spectrum. Well, what's a response spectrum in earthquake? On one hand, we assume or measure or take from somewhere a certain run of accelerations of an earthquake. It oscillates some way. And then we have a defined single mass oscillator to which we apply this earthquake. And the response of this single degree of freedom oscillator, that's what we call a response spectrum. It's the response of this oscillator to the given earthquake. And of course, that varies quite a bit with the periods in which the Earth shakes. Even for the same acceleration, it depends how close we come to the eigenfrequencies of this pendulum. So, just to make you understand what we talk about if we talk about a response spectrum, that's what it is. It's quite high. We know already about the movement there, and this is some way to show in soil mechanics we prevent the shear failure in this deep plane, Grundbruch. We avoid by ascertaining that this slides before the shear failure here takes place. Quite an involved geotech investigation. Naturally, we have to look into the swinging tower. And that thing, depending on what frequency and accelerations we apply, oscillates in all directions and then has tension somewhere, which means cracked stage, which means less stiffness, which influences the eigenfrequency and the moments under a given deformation and all that. And if you do that carefully, and the French have done that, you have to do many runs and I think they checked 80,000 cross-sections for stiffness and sizing of reinforcement. If you do it real in detail, it's a very tedious work. Now, I've told you how we stabilize the tower head. How do we cater for the beam changes in length? We do that by having the beam over the full length of something 2.5 kilometers or so freely in the cables. There is no longitudinal connection between the beam and the towers. It's just like a swing, and it can swing like a children's swing in a play yard. Of course, we have 2-meter movement possibilities, movement joints at the end with bumpers. So in longitudinal direction, the beam is free, which gives it a low eigenfrequency, which makes it rather in that way that it doesn't feel, that it doesn't respond to fast movements of earthquake when it has this long period. We did this with a desired failure joint for the Pesco-Kennewick Bridge. I told you a long time ago, but so that is. However, in transverse direction, there we need something, not just bumpers that would take off the towers, but in transverse direction we have dampers, hydraulic dampers and springs and so on to dampen in transverse direction the beam. We see it here and there. It's all in more detail in the script. So, the second bridge I showed you, Rion Anterion, is special by its foundations, where a layer of gravel, unconnected, no pile connections between the foundations and the soil. There can sort of plastic sliding of this possible 2 meters difference can take place. That is real unique for this bridge. So, those were the series of cable-stayed bridges. Thank you.